Hello one and all, welcome to another online video by Einstein Academy. In this video, we'll be looking at learning outcome A from the topic of the periodic table from the JCH2 chemistry syllabus. Specifically, learning outcome A, trends and variations in atomic and physical properties for elements in the third period, sodium to chlorine, and in group 2, magnesium to barium, and group 17, chlorine to iodine. Candidates should be able to recognize variation in the electronic configurations across a period and also down a group. So to begin with, let's discuss a bit on the periodic table. So the periodic table is a table of chemical elements organized on the basis of their properties with elements arranged in increasing atomic number. So if you were to look at the periodic table, hydrogen has this number 1 here is the atomic number. This 2 is the atomic number of helium. So you can see that they are arranged in increasing atomic number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. And the atomic number is nothing more than the number of protons of that element. So if you have the same number of protons, you are the same element. If you have different number of protons, you are different elements. Okay, as simple as that. Moreover, the elements are also being put in the periodic table according to rows and also columns. So in the periodic table, if you are in the same row, you are in the same period. And if you are in the same column, you are in the same group. Okay, so this is what it means. The horizontal rows are called periods and the vertical columns are called groups. And there are certain properties as to why they are placed in the same period and certain properties as to why they are placed in the same group. And this is as illustrated in this next slide. In each period, the elements have a similar core of electrons with the number of electrons in the outermost shell increasing progressively by 1. Okay, so let me discuss this for a while. So for hydrogen, the number of protons is 1, and since it's electrically neutral, it will also have only 1 electron. Helium has 2 protons, so 2 electrons. So as you can see, the number of electrons also increase progressively by 1. Okay, but specifically, the number of electrons is in the outermost shell that increase progressively by 1 when you go across a period. So in order to discuss this better, we have to talk about how we construct electronic configuration first. And let me talk about that first before returning to this point. Okay, so let's talk about how do we construct electronic configurations. To be honest, this has already been covered in the topic of atomic structure. So this will be a brief recap. So these numbers here is really the principal quantum number. So we have principal quantum number 1, 2, 3, 4. Okay, and then this is the S block. This is the D block. And this is the P block. Okay, so and the way that you write out the electronic configuration is just to read the periodic table in order. Okay, so you go the lowest level energy orbital, principal quantum number 1, S. Okay, so 1s is right at the bottom. Then after that, you go in order. So although helium is placed here, it's in the noble gas. That's the reason that helium is placed here is because it's a noble gas and hence is placed in group 18. But for the purpose of writing electronic configuration, you can just consider helium to be here. So helium has 2 electrons. If we were to write the electronic configuration for helium, 2 electrons will be placed in the 1s orbital. Okay, so the next highest energy orbital will be principal quantum number 2s. Okay, so 2s, they exist in spheres, just to remind you. Then after that, principal quantum number 2p. And I remind you again that the 2p orbitals exist as a set of 3, px, py, pz. Then after that, principal quantum number 3, 3s. Then principal quantum number 3p. Again, existing as a set of 3. Then the next level will be principal quantum number 4, 4s. Okay, and then the next one will be, then you will hit the D block. And I would just like to remind you that the D orbitals here, although it's in the principal quantum number 4 row, it's actually the 3D orbitals here that we're talking about, right? Because in the principal quantum number 3, we actually have 3s orbitals, 3p orbitals, and also 3d orbitals. It's just that in terms of energy levels, when you fill up electrons, the 4s orbital is actually lower than that of the 3d orbitals. Okay, so the next lowest energy orbital will be the 3d orbitals, and they exist in a set of 5, dxy, dxz, dyz, dx squared minus y squared, dz squared. So if you have forgotten all the stuff, just go and look back at my previous lecture that I've made on atomic structure. And after the 3d orbitals, then if you go in order, it will be the 4p orbitals, which again exists in a set of 3. Okay, so basically, after you write out the energy levels of the orbitals, let's say we want to write the electronic configuration of magnesium. So magnesium has 12 electrons. We will put 1 here, the second one, 3, 4, 5. Okay, so now for the 6th electron, we can either pair it up or we can put it into a separate orbital. However, Hund's rule tells us that we'll put it in a separate orbital in order to minimize electronic repulsion. Okay, so this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so schematically, to write the electronic configuration of magnesium, it will be 1s2, 2s2, 2p6, 3s2. Okay, for a total of 12 electrons. And using this method, you'll be able to write the electronic configuration of any atom in the periodic table. Okay, but for the purpose of A level, most likely you will only be asked to write the electronic configuration of up to the transition metals up to zinc. Okay, there are two anomalies in the form of chromium and copper, and we'll just discuss this further when we do transition metals. Okay, so this is the way to write electronic configuration, and based on this way, we can write the electronic configurations for all the elements across period 3. Sodium will be this, 1s2, 2s2, 2p6, 3s1. Then magnesium has 1 more electron, so it's placed in the 3s orbital. Aluminium has again 1 more electron as compared to magnesium, and is placed in the 3p orbitals, so on and so forth. Okay, so having wrote the electronic configuration for all the elements across period 3, let's go back and discuss that point. Okay, in each period, the elements have a similar core of electrons, with the number of electrons in the outermost shell increasing progressively by 1. So it's certainly true that the number of electrons increase progressively by 1. The number, what does it mean to say the number of electrons have a similar core of electrons? The core electrons are basically the electrons that is not part of the valence shell. Okay, so these are the electrons that's in the inner core. Okay, because they are in the inner core as compared to the valence orbital. Okay, so these are the inner shell electrons, and if you look across all the elements in the same period, they will have the same number of inner shell electrons. Okay, so they only differ by the number of outermost electrons, increasing progressively by 1. Okay, so this is what it means to say that in each period, the elements have a similar core of electrons, same number of inner shell electrons, while the number of electrons in the outermost shell increase progressively by 1. Okay, in each group, on the other hand, basically columns, okay, so like vertical columns, the elements have the same number of valence electrons and thus the same outer electronic configuration. So if you were to use the method that we have discussed for constructing electronic configuration previously and construct the electronic configurations of all the group 2 elements, okay, not all, as in part of the group 2 elements, magnesium would have this electronic configuration, calcium would have this, so on and so forth. You can see that basically they differ in the number of inner shell electrons, because when you go from magnesium to calcium, right, there is an increase in the entire principal quantum shell. Okay, however, it is true that the number of valence electrons is exactly the same. And in this case, the number of electrons in the most outer principal quantum shell is exactly 2. And that's the reason why you're placed in group 2. Basically, if you're in group X, you have X number of valence electrons. Okay, so in each group, the elements have the same number of valence electrons. Group 2 have 2 valence electrons. Group X has X number of valence electrons. And thus, you have the same outer electronic configuration. And this is important because in chemistry, only the valence electrons participate in reaction. So if you have the same number of valence electrons, you will behave similarly in a chemical fashion. Okay, so more often than not, it's only important to know the group number of an element in order to know how it will behave chemically. Okay, so that's the important thing, basically the group number of any single element. If you go down group 17 again, like the number of valence electrons is here, because these electrons are in the most outer principal quantum shell. For bromine, it will be this and this that is in the outermost principal quantum shell. And this one will be this one and this one. And as you can see, if you add up the total number of electrons in the outermost shell, the valence shell, you will get 7. So chlorine, bromine, and iodine all have 7 electrons in the valence shell. Okay, so with that, I'm going to wrap up this video, and hopefully your candidates are now able to answer this learning outcome. So to be basically able to construct the electronic configuration of all the elements across a period and also down a group. Okay, if you have any questions, just drop it in the comment section. If you like the video, please hit the like and subscribe button. And in the next video, we'll be looking at learning outcome B from the topic of the periodic table from the JCH2 chemistry syllabus. So stay tuned and I'll see you then.